Um, Hello, dear students. Actually, we are starting the introduction to finite element method. Okay. In this regard, we sent some of the YouTube lectures of IIT Kharagpur, and apart from that, we also sending some of the video lectures about the fourth chapter called the Introduction to Finite Element Methods. Some of the introductions already we had given in the first chapter. What is the finite element method? What is its advantages, disadvantages, and applications? So, before starting this chapter, let me discuss about what exactly the definition of the finite element method. Okay, the definition will goes with like this: finite element method is a computer-oriented numerical analysis technique used to find solution to the physical problems whose behavior could be explained by means of equation of calculus. So with these definitions, we have so many things underlined here. Some of the words: okay, computer oriented numerical analysis technique, solution, physical problems, behavior, and equation of calculus. What is it actually? And everyone know that computer oriented numerical analysis technique are the software tools. The software tools as we are using right now in the lab is ANSYS. Similarly, we have Nastran, Abacus, Madimo, and so many softwares we have. And what is the physical problems here? Physical problems, you might be knowing, we have 3D elastic bodies, structures, and resonance problems and vibration problems. Okay, this can be solved by using this finite element analysis. Then coming to the behavior. So behavior, we know that stress strain behavior, okay, that is called the elastic behavior. We have the plastic behavior also, and rate dependent material behavior, and that means strain or displacement measures with respect to time, and rate independent problems also we can solve. So this kind of a behavior we can analyze, or we can analyze in the finite element softwares. Okay, and last this one is equation of calculus. Okay, so equation of calculus everyone knows it will be used to get a solution for the variable problems. Okay, because when we are formulating finite element method for 1D or 2D problems, you will be assuming a displacement function, okay, or a displacement equation, wherein we have the so many variables a0 plus a1x plus a2x square. Okay, if you do the some integration or differentiation, we can get the solution for those functionals or equations. Okay, that is called the equation of calculus. So in general, everyone know that for infinite degree of freedom problem, there won't be any solution. Okay, that's what I wrote here. For infinite degree of freedom problem, solution not exists. So to convert infinite degree of freedom problem into finite degree of freedom problem, the discretization is done in FEM. What is discretization? It is nothing but the dividing the given physical problem or region into finite number of elements. That is called the discretization. Hence, the finite element method came. Because of converting infinite degree of freedom problem into finite degree of freedom problem, the discretization is going to do. That's why the finite element method came into existence. Okay. So next we will go to the and this discretization can be done because of two things. One is because of irregular geometry. Suppose the geometry is irregular, or so many abrupt changes in the geometry. That's why we are going to do the discretization. And infinite to finite degree of freedom. Okay. So for this we have potential energy functional, and cannot be applied for all the irregular geometry. That's why infinite degree of freedom is. The potential energy function is applied for each individual element and then summed up to the get a overall energy equation. This already we seen in the Rayleigh method and the Galerkin method. Okay. Next, you know that procedure of finite element method. Okay, we have the region of irregular shape. Okay, the boundary. So wherein we have taken the triangular elements here. Okay, in the xy coordinate system. And the node numbering and element numbering scheme. Okay, you should know that how exactly we need to number. Okay, and you know that your this curve is approximating like a straight line. Okay, because the whatever the curve or the boundary we have, it consists of so many lines. Okay, so keeping in mind, so we'll be dividing this entire region into triangular elements. Okay, I divided. Okay, so many triangular elements. Okay, always while giving the node numbers, okay, you will give 1 2 3, you will put a circle over it. Okay, for the node numbers. For elements, you will put a number and you will put a circle. Okay, these are the node numbering and element numbering scheme in the finite element method. Okay, so next we will go to the steps in finite element method. Okay, this is one diagram prepared for this. Okay, what is the steps in finite element method? Okay, many times I told in the class what are the different steps in finite element method. Okay, in the laboratory classes also I said with respect to theory we have 6 steps. With respect to finite element software we have 3 steps. Okay, that means the remaining 3 steps we cannot see on the computer screen. It will happen behind the screen, that means in the processor. Okay, so now the different steps involved in the finite element method, this schematic diagram or a block diagram will show the how exactly the finite element method will work. Okay, that is in the classroom. So now we have the physical body and it is called the continuum also we can call. So we can fix it on bottom side and we are applying some loads. Okay, and next we will take the finite element approximation method because it is approximation method, and because the geometry is regular there won't be any error in the finite element discretization, and we are going to divide into n number of elements. Then element data we are going to supply. You know that what is the element data. Okay, so area, cross section, length. Okay, element data we are going to supply, and calculation of element stiffness matrix. Okay, that means this physical body we are going to discretize or divide into finite number of elements. All elements are here hexagonal elements. Okay, for that we need to derive the element stiffness matrix for one element. Okay, that is K into U equal to F. K is the stiffness matrix. It is always a square matrix, and U is the vector matrix for the element, and F is the force. That is, you know that stiffness equal to force per deflection. Same equation will be using here. Next, after deriving element stiffness matrix for one element, then how many elements are there? We are going to assemble that combination of element stiffness matrix. That is, here I wrote K superscript E, that for the one element, U into superscript E, and F into superscript E. That is, small e indicates the for one element you are deriving element stiffness matrix. Then in the next step we will be assembling all these element stiffness matrix. How many elements we divided? N number of elements, 10 element, 20 elements, like that. That's why we will be writing global stiffness matrix or a combination of element properties. That is Kg, global stiffness matrix, into Ug equal to Fg. Then to solve this matrix we will be applying some we will be getting some solution for that. Okay, solution of load and deflection. Okay, so Kg into U superscript G equal to F. Okay, so deflection can be find out K inverse 1 by Kr 1 by K into F into Z. Okay, so by doing so we will get the deflections. By invoking Hooke's law, sigma equal to E into epsilon, we can calculate the stress. And meanwhile, these are the boundary conditions. It is interlinked with the problem. Okay, so boundary conditions is it is fixed and you are applying the load here. This is a boundary condition. Those boundary conditions will be using in this equation to get a solution. Once if you got the deflection, okay, then you will be calculating the stresses by calling Hooke's law. relation, that is sigma equal to E into epsilon. Okay. Now, so this, based on this picture, we will write different steps in FEM. I said step 1 is discretize the problem region. Okay. Discretize the problem region. Okay. Discretize the problem region. So here, first step is, this means that the region is subdivided into finite elements. The elements and nodes are numbered and nodal coordinates are specified. Okay. When you do the discretization, so in each coordinate is a polar coordinate or a Cartesian coordinate. Okay. And then how many elements you have taken? You have to give the numbering 1, 2, 3, 4 for elements. I said for nodes, so there won't be putting any circles over the numbers. Only 1, 2, 3 were writing. For elements, you will be putting 1 and putting a circle over it. Okay. So like that, you are going to discretize the given physical problem. So this is first step. Okay. What I said is first step. Then we'll go to the next step. Next, selection of displacement model or a function. So that element data. Okay. This data is required. This means that some polynomial function which is approximate the element displacement, the order of approximation, the linear or quadratic, must be specified. Okay. So because every element it gives some kind of behavior. It's a linear behavior, non-linear behavior. Okay. So we should assume some kind of polynomial function or a trigonometric function to satisfy the given boundary conditions. Okay. With that regard, it may be a linear or quadratic behavior, but the order of the approximation, second order, third order, that should be specified very clearly. Okay. That is called the second step, selection of the displacement model or a function. Next step. Third step is, after selecting the displacement function or a model, so we need to derive the element stiffness matrix. Okay. Step 3 is derivation of element stiffness matrix. Okay. So the stiffness relates the nodal displacement to the applied forces or nodal forces. The stiffness matrix consists of coefficient of equilibrium equations derived from the material and the geometric properties of the element and obtained by the use of minimum potential energy principle. Already we know this. Okay. The relation between nodal force and nodal displacement and stiffness is expressed as KE into UE equal to FE. Okay. So in third step, what we are going to do is we are going to derive a element stiffness matrix. Okay. So the equation is, this stiffness equation will be using. Okay. So this in detail you will see in the next further classes. Okay. Next, step 4 is, after deriving the element stiffness matrix, so assemble of algebraic equation for the overall discretized continuum. Okay. This step involves in determining the global stiffness matrix. That means for one element you are going to derive the stiffness matrix. Next, you are going to assemble those matrix. Okay. Assemble those matrix and get a overall stiffness matrix. Fourth step is assemblage of element stiffness matrix or algebraic equation for the overall problem. Okay. So that is Kg equal to Uz equal to F. That is where Kg is global stiffness matrix, Ug is the global displacement vector matrix, Fg is the global force vector matrix. Okay. This is the fourth step. Next, fifth step is applying the boundary conditions. Okay. There are three methods of applying boundary conditions in FEM. Now you know that what is a boundary condition. In general, you are fixing the problem and applying the load card. Okay. So there is a methods we have in the finite element. One is the elimination method, and second one is penalty method, and third one is the multi-point constraint method. But as per your syllabus, we will be teaching these two: elimination method and penalty method. So next in the further classes, we will be explaining how exactly the elimination method and the penalty method. This is called the fifth step. And step 6 is to find the unknown displacement, stress and strains. Okay. Always in the finite element method, first information you are going to get the deflection, or first solution you are going to get the deflections or deformations at the different nodal points. Okay. Once if you know the deformations, you can calculate the strain. Okay. That is change in length by original length. Okay. And by using the strain, we can calculate stress by recalling Hooke's law relation. Okay. And you can calculate the reaction forces also. Okay. This is the overall 6 step is to get a unknown displacement, stress, strain, reactions, everything. Okay. So now I hope you clear about the steps in finite element method. Okay. We have the nice picture here, okay, that will tells about the how exactly the procedure of finite element method. Then followed by I told very clearly about the step 1, step 2, step 3, step 4, step 5 and step 6. Okay, I will repeat again. Step 1 is discretization or dividing a problem into a number of regions. Step 2 is selection of the displacement model or assuming displacement function or equation for the element. And the third step is derivation of element stiffness matrix. So wherein you will be deriving the element stiffness matrix for the what element you have chosen for dividing the problem. And fourth step is assembling element stiffness matrix for all the elements, how many elements we have. Then fifth step is applying the boundary conditions. You are using the elimination method, penalty method and multi-point constraint method. But as per our syllabus, we will be discussing only elimination method in the penalty method. And in the sixth step, we'll be finding the unknown displacement stress strain. Okay, that again, once if you know the displacement after solving the stiffness matrices, so by calling or invoking Hooke's law, we can get the stress and strains. Okay, this is about the different steps in finite element method. So now these 6 steps, if we discuss in detail during this remaining whatever the lecture hours we have, so that is the finite element method. Okay, I think we may get how many number of classes based on the 18, 20 classes we may get. Okay, within the 20 classes, if we discuss in detail about these 6 steps, what is the first step, second step, third step. Okay, so we will cover entire this finite element method. Okay, now discretization. First we will go with the first one, discretization of the given continuum or a body or a physical problem. Okay, so here I said for dividing we need an element. Okay, so again we have in the basic elements, that is called the lower order element and the higher order element. Okay, so let me take here 1D element. So it is 1D link what we saw for a bar element in the laboratory classes, that is 1, 2. So at the extreme ends we have the points 1 and 2. And a 2D element, and these are all the basic elements are a lower order element or a primary elements. 2D element or a triangular element 1, 2, 3. So there will be a 3 points here, 1, 2, 3 at the extreme ends. Okay, and if you take the 2D quadrilateral element, we have 1, 2, 3, 4. Okay, 4 elements are quadrilateral element. Then 3D elements, tetra element you take. So 1, 2, 3, 4. This basic element nodes only we have. That's why basic elements are lower order elements. Then 3D brick element or a hexa element if you take. So many nodes? 8 nodes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are all the basic elements are lower order elements. Okay, now in this we have higher order elements also. Other than the basic nodes, that is minimum number of points required to make a line or a triangle. Okay, that is called the basic nodes. Other than the basic nodes, we are defining the elements are called higher order elements. For example, if we take, so if you put only 2 nodes, it is a lower order element or a primary element or a basic element. If you introduce a middle node here, okay, this becomes a higher order element, that is 1, 2, 3. So entire this is one element, not 1 and 2. Okay, there will be 2 elements here. Okay, only one element, we have 3 nodes. So numbering scheme is 1, 2, 3, like this. You can't give 1, 2, 3 like that. Okay, 1, 2, 3, higher order link element. Similarly, if you take a triangular higher order element, basic nodes is 1, these corner nodes are 1, 2, 3. Okay, so 1, 2, 3, 4, 5, 6. So basic nodes is 3 and mid side nodes is 3. Totally 6 higher order 2D triangular element. Similarly, higher order 3D tetrahedron element, hexahedron element, like that we have. Okay, in FEM, it is not necessary to discretize the entire body or structure. For this, we are considering the symmetry of the structure based on the geometry. Okay, So what it means is, in the sense what I am telling is, so here in the FEM it is not necessary to discretize the entire body for a given body. Okay, so suppose if the cylinder, okay, or if it is a turbine blade, okay, like that, we can consider some kind of symmetry, axis symmetry, planar symmetry, like that. Okay, so that means we can reduce the computational time instead of dividing entire physical body. So we can reduce the computational time here by considering the symmetry. Okay, that's why hence the four types of symmetry conditions are used to model the structure. Okay, so why this symmetry is to reduce the computational time and will be simplifying the problem from complex to simple. Okay, so that's why the entire body we're not going to discuss in the FEM. Okay, that's why let me take one planar symmetry. That is, if it is 2D plate we have. Okay, 2D plate with a hole at the center. Okay, then it is subjected to some tensile load, and suppose if you divide this one into a number of elements, you can imagine how many number of elements you want. Okay, instead of that, only this 1/4 of the plate you can take and you can divide, and you give the symmetrical boundary conditions, and you can solve. Later you can expand and you will get the entire problem behavior. Okay, so this kind of planar symmetry will solve this type of problem in the laboratory next. Okay, then axis symmetry. Similarly, you can see the cylinder, solar cylinder, let us take. Okay, so this is the coordinate system here. So only this part you can take and you can revolve about z axis, you will get the cylinder. Okay, is it right? Because this remains same. Okay, that's why we need to discretize this part and apply the boundary condition, then revolve. Okay, then there is an option in the revolve in the this one ANSYS, okay, or in the any kind of FES softwares. Okay, so that you can get the entire cylinder and you can get the behavior of the cylinder with subjected to some internal pressure or any load, like that. Okay, so this is called the axis symmetry. So one more example is this is called the axis symmetry cylinders. Okay, then one more symmetry is cyclical symmetry. Okay, you can see the cyclical symmetry here. Fan turbine blades, I said. Okay, all the blades are subjected to the same kind of pressure or force. Okay, that is in the RZ coordinate, R theta Z coordinate, the polar coordinates. Okay, fan blades or turbine blades you can analyze. If analyze for one blade, it is more than sufficient, because the behavior remains same in all the blades. Okay, because when the blade is rotating, okay, at a certain speed, then the forces exist in all the blades are remains same. Okay, that's why for designing only one blade, you can analyze what are the deformation stresses in the blade due to the pressure. Okay, that is called the cyclical symmetry. Then fourth one is repetitive symmetry. Just you can see the windows of aircraft or a train. Okay, so all the windows are subject to the same kind of forces. Okay, only one window you can analyze and you can tell that, okay, these are the some of the behavior, some of the behaviors due to the application of load. This remains for all the windows. If any geometry changes, then you can think of. Okay, so these are the some kind of symmetrical conditions, symmetric conditions you are going to consider before discretization. Okay, so as an engineer, you should look into the physical problem, and if the problem is symmetry, then definitely you could able to take these four kinds of, anyone can take among these four kind of symmetry, then you can simplify the problem so that you can save your computational time and you can get the results quickly. Okay, then coming to the second step is selection of displacement model or a function. There are two kinds of functions that could be assumed in the Coordinate element method. One is a polynomial function, trigonometrical function. Okay, so here let me go with the polynomial function only. If we take trigonometrical function, somewhat it is complex in solving the problems. Okay, out of the two functions, the one that is preferred for FEA is a polynomial function for its ease of mathematical calculations. Okay, because when you do the differentiation and integration, the polynomial function is somewhat easy, or it is very comfortable rather than the trigonometrical function. Okay, the displacement model selected is governed by the condition, the type of and the order of functions. Okay, the model selected should give the specific and meaningful displacement it denotes. The displacement model selected should satisfy the certain conditions called the convergence conditions. Okay, so these are some of the conditions the displacement function should satisfy. Okay, these are the first is second step, and that is I said it is before going to third step. Again I will repeat, second step we will be assuming some kind of polynomial function. Okay, so some kind of function. So I said we have two methods, one is polynomial and trigonometrical function. Always will prefer polynomial function only because it is very easy to get a solution and you won't get a more error by taking the polynomial function. If you take this trigonometric function, then it requires a lot of mathematical formulas and all. Okay. So this video will stop here. Then next we will take up one more video, derivation of element stiffness matrix, that is third step in FEM. Okay, so in this what I will do is I will take one example of a simple 1D element, then we will be deriving the element stiffness matrix. Okay, because this is very very important. If you know the derivation of element stiffness matrix or a formulation of 1D element, nothing but then you can solve the problems on this. Okay.